Okay, so starting with Chapter 7, we're going to take a look at applications of definite integrals. So as we know, the integral represents the area under the curve. However, it also has some real-world applications. So in this first part, we're going to take a look at some familiar functions, velocity, we'll look at displacement, final position. But when we worked with them earlier, we started with position, and then we found the derivative to find velocity. We did the derivative again, and we found acceleration. Well, just like if we have position, let's say position, when we do derivative, we get velocity. We do the derivative again, we get acceleration. Well, what happens when we go backwards? It works the same way with integrals. So let's start with just a little bit of review. Particle motion. So if velocity is greater than 0, so if it's positive, it's moving to the right. If velocity is less than 0, it's moving to the left. Now we have our displacement. Now, if you recall back when we figured out displacement in previous chapters, we knew that it was the change in position. Well, think about when we integrate velocity. Okay, so working backwards, we get the position evaluated from A to B. So we have the final position minus the initial position. So we actually get that from integrating velocity. So displacement is the antiderivative for velocity. Final position, this is nothing new. That's your initial position plus your displacement. Or in other words, if I want to find the position, let's say at a particular time B, that's going to be your position at A plus the integral from A to B of v of t dt. So again, this is basically, this is here, your displacement. And then finally, total distance traveled. So total distance traveled, we want to count all of those places where we go backwards. We want to count that as a positive distance. So that's the integral of the absolute value of v of t dt. Okay, so just make sure you refer back to this first page if you get stuck on any problem. So example 1, the function velocity, the function v of t is the velocity in meters per second of a particle moving along the x-axis. So here we're going to find each of the following. So for part A, determine when the particle is moving to the right, to the left, and when it stopped. So we actually aren't going to use any calculus in this first part since we're already provided with the velocity from 0 to 10 seconds. So the first thing that we want to do is we want to set velocity equal to 0. Think of, when we found our critical points in previous chapters. So here we have 3t equals 24. So t equals 8. That's when velocity equals 0, so that's actually when it stopped. So it stopped at t equals 8. Now, when is the velocity moving to the left and to the right? We're going to create a number line. Now keep in mind, it starts out at 0 and ends at 10. And then at 8, we know it stopped there. So I'm going to label this as v, since that's my velocity function. Now I want to choose a test value between 0 and 8, say 1. Plug that into the velocity, and I get a positive. Plug in something between 8 and 10, say 9. So 24 minus 3 times 9 would be negative. So now I know it's moving to the right from 0 to 8. We're going to include zeros because actually 0 is, it's moving in the positive direction if we were to plug that in. At 8, it's changing direction, so that's why I use a parentheses around that. And then we would have moving left from 8 to 10. And again, we're going to include the 10 with a bracket because if we were to plug 10 in, that would still result in a negative. That's part A. So part B says find the particle's displacement for the given time interval. And then there's another question. If the initial position is 3 what is the particle's final position? Okay, so let's start off with displacement. Okay, so our displacement is, looking back above, it's from A to B of v of t dt. So again, I'm looking for over the given time interval. So from 0 to 10, 24 minus 3t dt. So 24t minus 3t squared over 2. And we want to evaluate that from 0 to 10. So I have 24 times 10 minus 3 times 10 squared divided by 2. So we should get 90. And this is measured in meters per second, so 90 meters. In other words, it's positive, so that means we ended up 90 meters to the right from where we started. Now the second part of that question says, if s of 0 equals 3, what is the particle's final position? So your final position, looking here, it's initial position plus displacement. So I'll write it out so you can see it's s of 0, and then the integral from 0 to 10 v of t dt. Well, s of 0 is 3. This integral we just evaluated. We found out that that was 90. So our final position is at 93 meters. Okay, the last part, total distance traveled. So your total distance traveled, we want to take the integral of the absolute value of v of t dt. Again, this is from 0 to 10 seconds. Now, you can actually evaluate this by hand. What you would have to do is you'd have to separate this into two different integrals, because keep in mind when it's from 0 to 8, it would be positive. And then from 8 to 10, because the velocity is negative, you would have to evaluate that and then make it positive. However, to make your life easier, I'm going to allow you to just use your calculator. This chapter test, chapter 7, is going to be all calculator okay, which means that the setup of the problem is going to be the most important. So you're going to show me the initial setup. There are some cases where I do want you to practice evaluating the integral for practice, but something like for part B, total distance, I would be fine with just going to the math 9. We're going to type in 0 to 10. Oops. And then to get the absolute value, remember we go to math, go over to number. Number 1 is absolute value. We're going to type in 24 minus 3t. Use x is fine. dx. And we get, looks like 102 meters. Next example. So this is another one, same exact kind of question. Here we have the velocity of the particle, determine when it's moving to the left, to the right, and when it's stopped. Particle's displacement. Here, if f of 0 equals 1, what is the particle's final position? And finally, C, what's the total distance traveled? So the only difference between this and the last one is this one we have a trig function. But for part A, we're going to start out the same way. We're going to set sine of t equal to 0. Now, where is sine equal to 0? Between 0 and 2 pi. So we picture when t equals 0, t equals pi, and when t equals 2 pi. So right here, that's when our particle is stopped. Now let's make a number line. We have 0, pi, 2 pi, and again, this is velocity. Again, those three places are where it stops. So if we pick something between 0 and pi, say pi over 2, sine of pi over 2 is 1, which is positive. Plug in a test value, say 3 pi over 2, sine of 3 pi over 2 is negative 1, So our particle is moving right from 0 to pi, and it's moving left from pi to 2 pi. Now I'm using parentheses for both of these because actually at all of those endpoints, at 0 and at pi and at 2 pi, the particle happens to be stopped, so I don't want to include that in my interval. Okay, for part B, let's find the displacement. So displacement is going to be the integral. Again, we want from 0 to 2 pi, that's our interval, and then we want sine of t dt. So the antiderivative for sine is negative cosine. So we have negative cosine of 2 pi minus negative cosine of 0. So here, that's going to give us a negative 1 plus 1. We get a displacement of 0. Our final position, or in other words, the position at 2 pi is going to be the initial position plus the displacement, which is the antiderivative, from 0 to 2 pi of v of t dt. So in this case, our initial position was at 1. So I have 1 plus, and our displacement was 0. Oh, I forgot to put units in here. It's meters per second again. So this time I get 1 meter. And last, we have part C, total distance traveled. So our total distance is going to be the integral from 0 to 2 pi. And then we put absolute value of v of t dt. So we'll go here. Math 9, 0 to 2 pi. Absolute value, sine of x, dx. And I get 0.344, I believe. Yeah. Okay, next we have example number 3, a car moving with initial velocity of 5 miles per hour. So v of 0 equals 5. Accelerates at the rate of a of t equals 2.4 t miles per hour per second for 8 seconds. Part A says, how fast is the car going when the 8 seconds are up? So this is actually a very similar question. It's just asking, instead of final position, we're actually asking, in this one, final velocity. What are we given? We're given initial velocity, and we have acceleration, which was 2.4 t. So we want to find the velocity at 8 seconds. So we're going to start with the initial velocity plus the integral from 0 to 8 of a of t dt. So here I have 5. Now we want to integrate 2.4 t dt, which is our acceleration. So we have 5 plus, this is going to become 2.4 t squared over 2, or 1.2 t squared. And we want to evaluate that from 0 to 8. So I have 5 plus 1.2 times 8 squared. So we plug that into our calculator. So we get 81.8. Now, you'll notice here in the phrasing, it said this acceleration was miles per hour per second for 8 seconds. So when we integrated, that basically gets rid of this second. So we're just left with miles per hour in the end. So it's 81.8 miles per hour. Now that's actually just one way to solve this problem. Another way that we could have solved this is we could have worked backwards, started with acceleration, and I'm going to show you what that looks like in part B, because it says how far did the car travel during those 8 seconds. So what we're going to have to do for part B is we need to find out the total distance traveled. So in order to do that, right, this is total distance. So how do we find total distance? Well, we're going to have to integrate the absolute value of v of t dt from 0 to 8 seconds. But I don't have the velocity function. But can we find it? So let's talk about velocity. Velocity is going to be the antiderivative for acceleration. Well, if we integrate 2.4t dt, I get 1.2t squared plus c. Now, why didn't I use bounds? Because I'm looking for the function v of t dt. So I don't want to necessarily put in bounds here. This function I want to represent for any time. Now, can I solve for c? Sure. What were we provided? We have v of 0 equals 5. So I know 5 equals 1.2 times 0 squared plus c. So c is 5. So here's our velocity function. Now, well, that's always going to happen if that's our initial velocity, but I wanted to show you, because sometimes we don't have the initial velocity. Sometimes we have the velocity at 3 seconds. Could we solve for c? Sure, same process. So here's my velocity. So my total distance traveled. Now I can't find my position function because I don't know the initial position, but we don't need to know because our total distance traveled is going to be the integral from 0 to 8, absolute value of 1.2t squared plus 5 dt. So we're going to plug that in. So math 9 from 0 to 8. Then we have math over to absolute value 1.2 x squared plus 5 dx 244.8. Now, here's the question. How far did the car travel during those 8 seconds? What are the units? Notice this now, velocity would be measured in miles per hour, right? That's what we got from part A. The problem here is the units aren't matching up. These units are in seconds. So there's a couple things that we could have done. We could have changed the seconds to hours, or when we're done, we can change the units here by dividing by 3,600. So in other words, I could have divided my upper and lower bound. Obviously, the lower bound wouldn't be affected here. So I could have changed these. Again, since this is miles per hour, I want these units to match. If you don't want to do it there, you could do it later. So if I change this, let's see what we get. We get 0.068, and this is miles. So each time we integrate, we get rid of that last, the time unit. So if it's miles per hour per second, the first time we integrated, it got rid of this per second. Second time we integrated, it would get rid of the hours, except that the units weren't in the same, one was seconds, one was hours. So we had to convert either when we were integrating or after we integrated. Now, if you want to change that to feet, you would just multiply by 5,280 feet. which would give us about 359.04 feet, or you can keep it in miles, that's fine. Okay, so another way we can look at integrals is total consumption over time. So this is a way to calculate net change or total accumulation other than just distance and velocity. So you can calculate growth, decay, consumption, and basically anytime we have a rate, we're going to integrate it and that will find the total amount. So example 4, from 1970 to 1980, the rate of potato consumption in a particular country is represented by C of t equals 2.2 plus 1.2 t millions of bushels per year. With t being, this is important, t is the number of years since the beginning of 1970. So in other words, t equals 0 when it's 1970. T equals 10 when it's 1980. This is important because it's going to affect our limits of integration. Because let's read the next question, or the question says, how many bushels were consumed from the beginning of 1972 to the end of 1973? Set up the integral and then use a calculator to evaluate. So from 1972, well, if t equals 0 when it's 1970, then t equals 2 at the beginning of 1972. Now, the end of 1973 is the same as beginning of 1974, right? Since this one says beginning, we want this one to be the beginning. So for that, t is going to be equal to 4 because that's going to represent the number of years, again, since the beginning of 1970. So this is going to be our upper limit of integration. So from 2 to 4. And then we're just going to put in our function. So 2.2 plus 1.2, sorry, 2.2 plus 1.1 to the t dt. And from here, we get to just plug that into our calculators. So math 9, 2 to 4. And then we have 2.2 plus 1.1 to the x. And then we have dx. And we get 7.066 millions of bushels. So over that time, that's how many total bushels were consumed. Okay, example 5. Here we have the velocity of a particle moving along the x-axis is given. So the particle starts at x equals 2 when t equals 0. So s of 0 equals 2. We want to find the particle at the end of the trip. Now, it says y here, but this is actually velocity. In other words, we're looking for final position here. So final position, or the position, again, it looks like it goes to 10. So we're looking at s of 10 equals s of 0 plus the integral from 0 to 10 of v of t dt. So just like what we were looking at before. So our initial position is 2. Now, the integral for velocity. What we're looking at is the region above and then the region below. Now keep in mind, this doesn't have an absolute value. This is the displacement. So we want to count anything above the x-axis as positive, anything below the x-axis as negative. So here I have, I'll do the trapezoid first. So it looks like the height is 2, so h over 2, 2 over 2. Base 1 is 3. Base 2 is 6. I'm going to put in a subtraction sign. This time I'm going to look at this triangle. It has a height of 2. So 1/2. Base is 1, 2, 3, 4. So base is 4, height is 2. Again, I have to subtract because that goes below the x-axis. So here I have 2 plus 9 minus 4. So we should get 7. Now for part B, we want total distance. So the total distance traveled is going to be the integral from 0 to 10, absolute value of v of t dt. Now, we don't care about the initial position, we just want the area of the two regions. So we have the trapezoid plus, so now we count that triangle as a positive area. So we get 9 plus 4, so the total distance traveled is 13. Okay, last example. Okay, so, and this should actually look familiar because we did this back in chapter 5. A pump connected to a generator operates at a varying rate, depending on how much power is being drawn from the generator to operate other machinery. The rate, gallons per minute, at which the pump operates is recorded at 10-minute intervals for 1 hour, as shown in the table below. How many gallons were pumped during that hour? And we're going to use the trapezoidal rule to approximate. So, if we look at these time intervals, they're all evenly distributed. That's going to be our height. Our height is 10 minutes. So 10 over 2. Since they're all evenly distributed, we use the first one and the last one once, and all the ones in the middle twice. And if you don't like to use the trapezoidal rule this way, you can actually set up separate set up different trapezoids, separate trapezoids, and that should also work. So here I have 5, and I have 58 plus 2, and then I'm going to actually add all my okay, double check my work, 3575. Make sure that's what you get. And so we compare the units. So notice this was measured in minutes. This was measured in gallons per minute. So that means once we integrate, we are just left with gallons. So that's the total number of gallons that went through the generator.